welcome to this explainer. Today, we're unpacking a genuinely fascinating challenge. We are going to look at how to run massive 128,000 token context windows locally, entirely on standard consumer hardware. Now, normally, attempting to run 128,000 tokens of context is just flat out impossible on a home setup. It's a workload that traditionally demands massive data center GPUs packed with specialized memory. But today, we're exploring exactly how to deploy Google DeepMind's Gemma for E4B model on an AMD Strix point machine using Felium and Roxium. So, if you've ever wondered how to squeeze a massive reasoning engine onto a 16GB class memory budget without the whole system just grinding to a halt, you are absolutely in the right place. Let's dive into this.
Here's our roadmap for this explainer. We'll start with meet the Gemma 4 E4B. Move on to the 128K context secret. Look at the Strix point setup, explore multimodal capabilities, and wrap up with tuning and performance.
So let's jump right into section 1. Meet the Gemma 4 E4B. To really grasp this model, we first need to define why it's called an effective 4B model in the first place. That E stands for effective parameters, and the secret sauce here is something called per-layer embeddings, or PLE. Basically, each decoder layer in the model carries its very own small token embedding table. Crucially, though, this table is consulted via a simple lookup, not an active matrix multiplication. Think of it like looking up a word in a physical dictionary, instead of mathematically calculating its meaning from scratch every single time. What this does is brilliantly create a hard separation between memory and compute. Yes, the static memory footprint increases. You should plan for about 8 to 10 gigabytes for half precision, but the actual compute requirements stay impressively low. It acts like a standard 4.5 billion parameter model. You get this immense representational depth, but you aren't paying for it in flops or the raw computational crunching power that normally eats up your hardware. When we actually map this onto our hardware ecosystem, specifically targeting something like the Minis Forum AI-X1 Pro, we see a really clear division of labor. You've got the Ryzen AI 9 CPU managing the VLLM scheduler and tokenization. Then, the heavy lifting, the matrix multiplications, those are strictly isolated to the Radeon 890M iGPU. Meanwhile, the XDNA2 NPU sits in reserve as a sidecar, which we'll actually get back to later. And tying this entire thing together is the Unified Memory Architecture, or UMA. This is absolutely critical. It means our CPU and our iGPU aren't fighting over separate, isolated memory pools. They share this massive 64GB canvas, holding both our static weights and our key value, or KV, cache in total harmony.
Which brings us to section 2, the 128K context secret.
Okay, now we tackle the real mystery here. How is it mathematically possible to fit a 128,000 token context window on a standard consumer memory budget? It actually comes down to a highly specialized hybrid architecture. Traditional, full global attention scales quadratically, meaning the longer the context gets, the more aggressively it just devours your memory. But Gemma 4 relies heavily on sliding window attention, or SWA, and for Gemma 4, this window is capped at just 512 tokens. You can kind of think of sliding window attention like only needing to remember the last few paragraphs of a conversation, rather than memorizing the entire book verbatim. Once a sequence passes that 512 token mark, every SWA layer's KV memory cost becomes constant. It literally just stops growing. I actually love how the source material puts this. They say, most of Gemma 4 layers stop paying KV per token once you cross the window. That is the key takeaway right there. Only a few specific, periodic, global layers in the entire model actually continue to pay that KV tax over long contexts. Because the sliding window is handling the vast bulk of the layers, your memory growth shifts from the steep, punishing quadratic curve to a very gentle linear slope. And that is exactly what makes massive context windows entirely feasible on your local machine. And those few global layers, oh, they are heavily optimized. They utilize unified K and V projections. That means the exact same projection matrix produces both the keys and the values, which instantly halves the cache size for those specific layers. Halves it! Plus, they use proportional rope, or P-rope. This applies rotation to only a fraction of the head dimensions, leaving the rest completely untouched as an identity channel. Think of proportional rope like a lighthouse beam. It allows the model to compress its focus and maintain a really clear, strong signal over extreme distances, all without the attention mechanism getting diluted across tens of thousands of tokens.
Let's move from the theoretical math over to practical execution in section 3, the Strix point setup.
When we dug into the actual setup for this, we found that a highly precise environment is required to run it stably on AMD hardware using VLLM. So here is the actionable verified launch sequence for the GFX 1150 architecture. First, you absolutely must set the HSA override to 11.5.0 to target the RDNA 3.5 ISA. Second, disable SDMA. This one is crucial. It stops copy engines from racing the CPU on the shared bus. If they race, the system chokes and you get a complete system hang. Third, force the kernel arguments right into device memory to avoid faults on UMA architectures. And once all those are locked in, you can finally launch the VLLM ROSM container. But wait, before you pull that container down, there is a massive pitfall here you have to avoid. You must use the upstream image VLM-OpenAI-ROC, specifically version 0.20.1 or later. Do not use the ROCm/VLM dev image. That developer image targets AMD Instinct data center accelerators. It does not target your consumer Strix Point iGPU. So if you use the wrong image, your deployment is going to crash right out of the gate. With the model actually running smoothly, let's explore Section 4, multimodal capabilities. What is super interesting about Gemma 4 is how dynamically it handles images. It actually lets you adjust your visual token budgets to perfectly match whatever task you're doing, which is an amazing way to save precious memory bandwidth on your iGPU. If you're just classifying an image or maybe processing dense video frames, you can drop the budget all the way down to just 70 tokens. For general visual Q&A, around 280 tokens is the sweet spot. But if you need OCR, complex document parsing, or really fine-grained dense detection, you can crank that budget all the way up to 1,120 tokens. However, there is a catch if you're planning on customizing this model. It's really tempting to train high and then serve low just to save compute, but the data clearly shows the output quality will measurably degrade if you do that. So the critical rule of thumb here is you must fine-tune at the exact same budget you intend to serve at. Always match your training and serving environments. Beyond just vision, the model boasts some incredible native capabilities. It supports full audio understanding with automatic speech recognition across over 100 languages. It natively supports function calling, which means it rewrites inputs seamlessly into the standard OpenAI tool call shape. And it features a really powerful configurable thinking mode. Just one super important operational note on that, though. If you enable thinking, you absolutely must strip those thought blocks from your chat history before you send the next message. If you leave them in there, the model starts confusing its own internal scratchpad with the actual user conversation, and that severely degrades its multi-turn reasoning quality.
All right, let's move to our final act, Section 5, Tuning and Performance. Let's talk scale for a second. 131,072. That is the staggering maximum context length of this model. But, just because you can doesn't mean you always should. While the hybrid attention makes this massive length cheap to run, pinning your daily conversational workload to a maximum model length of around 32,000 tokens is really the sweet spot. It gives you plenty of room for robust prefix caching, which basically just means storing the beginning of the conversation so the model doesn't have to reread it every single time, while still maximizing your overall memory efficiency for other tasks. And what about speed? Well, when we look at decode throughput on the Radeon 890M, we see a fascinating bottleneck. Text generation decode is strictly memory bandwidth bound on an iGPU. What this actually means is the GPU is so incredibly fast at math, it literally ends up sitting around twiddling its thumbs, waiting for data to arrive from the RAM. So if you're getting under 5 tokens per second, your setup is broken. It's probably falling back to the CPU. 5 to 7 is suboptimal, but a perfectly healthy setup running standard half-precision FP16 weights is going to max out right around 7 to 11 tokens per second. That's just the physical speed limit of the memory bandwidth for data of this size. But you can absolutely break through that ceiling. By utilizing AWQINT4 quantitation, which essentially just means mathematically rounding the model's weights so they take up less physical space, you can shrink the footprint down to about 4 gigabytes. And because you are moving far less data through the memory bus, you can effortlessly double your throughput. With AWQINT4, you can jump from 11 tokens a second up to 18 tokens per second. It makes the model feel incredibly snappy while simultaneously freeing up tons of space for your KV cache. Finally, what is truly amazing for you power users out there is how we can route tasks to utilize the entire system. Remember that XDNA2 NPU we mentioned back on the hardware map? Well, VLLM doesn't use it natively. But by using MyGraphX routing, you can actually offload non-interactive, high-throughput one-shot inferences straight to the NPU sidecar using INT8 Onyx models.
One-shot inferences are basically just background tasks that don't require an ongoing back-and-forth chat. Think sentiment analysis or bulk image classification. This lets your CPU and iGPU handle the complex interactive chat smoothly via VLLM, while the NPU quietly chews through your background data tasks in parallel. It's brilliant. So, we've covered the architectural math, the unified memory mapping, the precise Docker setup you need, and the quantization tuning required to make all of this hum. You now have everything you need to intuitively run a multimodal AI right there on your desk. Now that you can run a massive 128,000 token frontier AI entirely on your local consumer hardware, what boundaries are you going to push first? Thanks so much for joining me for this explainer, and I will catch you in the next one.